Okay, so we're going to talk about reflections across the x-axis and across the y-axis, as well as vertical and horizontal dilations. To talk about reflections, we're going to first talk about the x-axis because that's the most common one. To do a reflection across the x-axis, you just have to put a negative sign out in front of the function. So we're going to start with a parabola or a quadratic function. So here's my quadratic function, the parent function, which is y equals x squared. And then I'm going to place a negative out front, and we're going to see a reflection across the x-axis, which means that it's just going to make a mirror image across the x-axis. So when I press that, all of a sudden now you can see that this is the exact same graph. It's just been flipped over the x-axis to create a mirror image. Anytime you're trying to do a reflection, it's as simple as making the function go from positive to negative. So then if we talk about a reflection across the y-axis, we're going to look at a cubic function. So here's my parent function for a cubic function. And for the y-axis, you actually have to input a negative x value for all your x's in the function. So since this is just the parent function, we only have one, so I'm going to input a negative x. And you see how it actually flipped across the y-axis and created a mirror image. So that would be a reflection across the y-axis. Okay, but I want to talk about multiple transformations together. Okay, so I'm going to put back my parent function of my quadratic, and I'm actually going to look down at number 5, and we're going to talk about the different transformations. So the first thing that I see that is different is I have a negative outside of my entire function. So that means that I should be looking for a reflection across the x-axis because the negative is outside of the entire squared. Also in parentheses, I have a minus 2.5, which means that that's going to be a horizontal translation. And since it's a minus sign, it's going to be the opposite, and I'm going to move to the right 2.5 units. So if I look, I have a reflection across the x-axis, and then I move to the right 2.5 units. Okay, if I look at number 6, I have a negative out front of just my x squared, but then I'm going to move it up 2. So I'm going to move my parabola up 2 units, and then I'm going to reflect it across the y equals 2 line. So if I didn't reflect the graph, or the green graph, I actually moved the green graph up 2 units. So I actually did this. I did x squared plus 2. I had the orange, and then I reflected that orange graph over and created the purple graph. Okay, so now let's move on to horizontal and, we're going to talk about rational functions. So here's my parent function for a rational function, which is 1 over x. Okay, again, I have a negative out front, so I know that it's going to flip over the x-axis, and then I have minus 2 at the end, so it's going to move down 2 units. So this curve that's on the left side and then in the third quadrant, that's actually going to flip up to the second quadrant, and my curve that's in the first quadrant is going to flip to the fourth quadrant. Okay, but I'm going to move the whole thing down 2 units, and you can see that I'm moved it down. Their asymptote is now occurring at y equals negative 2 rather than y equals 0. Okay, here's where we have a negative on the outside. So again, it's going to flip. Okay, but that x plus 4, that's like a horizontal translation, so it's going to move to the left 4 units. So you can see that my middle, I have another asymptote. Instead of at x equals 0, I have an asymptote at x equals negative 4. And again, they flipped. My black curve that was in the third quadrant flipped up to the second quadrant, and my black curve that was in the first quadrant flipped down into the fourth quadrant. Okay, so let's talk about dilations. So vertical and horizontal dilations are very, very similar. In fact, it's almost the exact same thing. It's just how you describe it. So a vertical stretch or a vertical expansion is the same as a horizontal compression, and a vertical compression is the same as a horizontal expansion. So I want you to think of the vertical stretch or the vertical expansion that's where it's going to get really skinny. So it's like when you put your hands in the air and you stretch in the mornings, you get skinnier and you stretch. Well, if we took something and we horizontally pressed it together, you would make it skinnier, okay? So the vertical stretch and the horizontal compression are the exact same thing, essentially. And then if you have your arms up and you go to, hug somebody, you typically move your arms out. So that's your vertical if you put your hands in the air and somebody were to press down on your arms would go down and you would get wider. So that's like your vertical compression. Well, if you took something and you horizontally stretched it out, you would make it wider. So your vertical compression, pushing your arms down, and your horizontal stretch are the same thing. Okay, and when we're looking at dilations, we're looking at the A value, or the number that is in front, the leading coefficient. Okay, so if we're going to talk about an x cubed function. Okay, my current leading coefficient on this number 11, the x cubed, is 1. Okay, all your parent functions have a leading coefficient or an A value of 1. When your A value, and we're not talking about if it's positive or negative, because the positive or negative goes with the reflections. When we're talking about dilations, we're only talking about the absolute value of the A value. So, like for number 12, the A value is now 1/4. So if you're saying it's a vertical dilation, then 1/4 is a compression because it's a fraction. It's less than 1. Okay, but it always has to be greater than 0 because we're only looking at the A value as a positive number. Or you could describe this as a horizontal expansion. And if you look, now that flat area near the origin looks longer. Okay, so it looks like you took it and horizontally stretched it, or it looks like you came and you pushed on the sides vertically and made it squishier and fatter. Okay, so let's look at number 12. So number 12 goes with a quadratic. So I'm going to turn on my quadratic parent function. Oh, I'm sorry, number 13 goes with a quadratic. Okay, so I have a negative out front. That negative tells me that it's going to have a reflection. But my actual A value is 0.2, which is less than 1 but greater than 0. So I either have a vertical compression or a horizontal stretch. So if I turn that on, horizontal stretch, it's wider, or it's like a vertical compression where somebody pushes down in your arms and it gets wider. And there's also that reflection that goes with it. Okay, number 14 is a rational function, so I need to turn on that parent function. Okay, now my A value is actually 15, which is greater than 1. So this is either a vertical stretch or a horizontal compression. So it's going to get skinnier now, okay? And then there's also a +3, which means that there's a vertical translation up. So I went up 3 units, okay? And there's also the horizontal. So if you look in the first quadrant, my new black line, you can see that it went up my new asymptote is now 1, 2, 3 lines above where it was. So like if I zoom out, you can see 1, 2, 3. My new asymptote is going to be at y = 3. But you can also see that it's going to take a lot longer to get there. And that's because I have my A is greater than 1. Okay, so let's look at 1/5x. So my A is now 5. Okay, and so same thing, I have a horizontal compression or a vertical stretch. I'm sorry, I keep totally losing track, them being so similar. Okay, so last one, we're going to look at a absolute value function. So here's my absolute value parent function. I have a negative, which means it's going to be a compression. You know what? Let's actually just get rid of that negative. Okay, and so my 4 is my A value. So 4 is greater than 1, so I know it's going to get skinnier. So you can either call it a vertical stretch or you can call it a horizontal compression. And when I put it on, it's skinnier, okay? So really what you just need to know is that if A is greater than 1, your graph is going to get skinnier. And if A is less than 1, your graph